Hello students, I hope all of you are doing good. In this video, we'll discuss few more examples from NMR spectroscopy. The first question is an organic compound having a molecular formula C9H12 exhibits two singlets in 1H NMR spectrum, and among the four compounds we need to identify the correct one. So these are the structures for these four compounds. And as per the expectation from the question, we need to identify a compound that will show two singlets. So one by one we'll discuss the moieties and we'll identify their number of types of protons so that whether it is matching with the expectation. In the first compound, if you look these structure carefully, then we'll identify this compound is having a symmetry that passes to these carbons, and we are getting the information from this that the three CH3s over here, this CH3 it will give one kind of protons, and these two CH3s they are equivalent. So the six hydrogens belonging to these two CH3s will absorb at one particular chemical shift, and the protons, which are the part of aromatic skeleton over here, if you are seeing this is it is a symmetry. So these two protons they are identical, and therefore these two protons combinedly it will absorb at particular chemical shift, and it will be third kind of protons, and this one it is the fourth. So we are not expecting, because in this case we'll get that this CS3 this will give singlet, these two CS3s as we are finding again it will give this singlet. HA proton, both the protons they will couple with HB and they will give doublet, while this HB as this is having the two neighboring HA protons, so this will give a combinedly triplet. So in this case we do not expect this compound will give two singlets, so therefore this is not the correct choice. In a compound B, here we are observing the compound which is a non-symmetric, and therefore all the protons, if we draw the aromatic protons, we'll find that here in this case we'll have this is first kind of protons, this will be the second, this will be the third, this will be the fourth, this will be the fifth, and this is the sixth. So six types of protons will be observed in NMR spectroscopy. And in this case also we can say this CS3 will give a singlet, this CS3 will give a singlet, this CS3 will give a singlet at a different chemical shift. This suppose we'll number that HB, HA and HC. So this HC will couple with HB and it will give a doublet. HB proton it will give a doublet of doublet, and HA proton it will couple with HB and it will give a doublet. So this is not the correct choice. In compound C, again it is similar to B in this case. Again, if you look at the structure, this is a non-symmetric, and therefore all the protons over here, again they will give different types of absorptions. And in this case, again we'll find all these protons that belongs to the different chemical shifts, and six types of protons will be observed. Again, in this case, we'll observe this CS3 will give a singlet, this CS3 will give a singlet, this CS3 will also give a singlet. H, A, H, B, and Hc protons. Ha proton it will couple with Hb and it will give a doublet. Hb proton it will couple with Hc and Ha proton, so this will give a doublet of doublet. And Hc proton it will couple with Hb, so this proton will give a doublet. So this is again a not our choice. So only one option is remained. In the compound D, we are observing this compound is a symmetric. Either we are having the all the cases we can find this is having a symmetric nature. So all the protons or the aromatic skeleton over here, they are equivalent, and therefore we'll observe that we can label them as Ha because they are equivalent. So all the equivalent protons, that Ha protons, they will give a singlet. it will give also singlet, and it will give a singlet. That means these three protons at same chemical shift, they will give a singlet. And these three CS3s, that means in the first case, as we have seen, that the 3HA combinedly they will give a singlet, and this singlet will be corresponding for the three hydrogens. And these three CS3s, they will combinedly give a singlet, and that will be corresponding for the nine hydrogens. So the correct answer for first question is option B. In the second question, the 1H NMR spectrum in CdCl3 of which of the following four compounds remains unchanged upon shaking with the D2O? This particular question is based on a D2O exchange. D2O exchange is one of the techniques in 1H NMR spectroscopy where we are doing an exchange of hydrogen with deuterium. And as we know, we are having the two different types of uh, NMR spectroscopy, that is one H NMR spectroscopy and this deuterium NMR spectroscopy. And both the spectroscopies, they are having the different chemical behaviors. At the hydrogen and deuterium nuclei, both are since NMR active, but the thing is they are with the different magnetic properties. And this is the advantage, that when we are doing a substitution of hydrogen with the deuterium, we can easily identify the presence of such exchangeable protons in a compound. And the thing is, if we are doing a substitution of hydrogen by deuterium, they will be not observed in 1H NMR spectrum. And in the case of if we are taking a deuterium spectrum, the protons will be not observed in a deuterium NMR spectroscopy. So this is the basic understanding about D2 exchange and how it will be helpful to assign the exchangeable protons in NMR. Now the question is, in 1H NMR spectrum, as it is said, we are having the four compounds, and out of this we need to identify a compound that do not show a D2 exchange. So where do we expect the D2 exchange? Wherever we are having protons that are residing on either oxygen, nitrogen, sulfur, because these are, as we know, these are the heteroatoms, and protons on these heteroatoms, they are acidic enough so that they can get exchanged with the D2. So we are observing in the first case, at least it is attached with the OH, it will get easily exchanged with the deuterium, and the NMR spectrum of the deuterated compound, it will be different. And as per the expectation in the question, we are in the search of compound that will not get changed upon checking with the D2O. So this is not the choice. In a second compound also we are having this NH2, as these two protons, they are connected with the nitrogen, and again there is a probability that this will get exchanged with the D2O. So therefore the NMR spectrum of N deuterated compound, it will be changed. So therefore this is again our not a choice. In between the two options, that is C and D, we are observing there is no any heteroatom that is connected to the hydrogen. So therefore we may think that is it out of these two which will be the correct option. At the same time, we need to identify the thing that in a compound D, it is a very peculiar functionality, that it is a beta keto ester. And in this case, as we know, the alpha hydrogens, they are acidic, so they are more susceptible, so that they can show enolization, and enolization will lead to form the enol. Enol is a functionality which is containing alkene and the alcoholic functionality. So this alcoholic functionality, again, this OH can be converted into OD. That means proton can be exchanged with the deuterium, and therefore this compound, when we are subjecting with D2O, it will show a change. So this is also not our choice over here, and only the thing that is remain, that is, this is ester, where we do not expect any kind of proton exchange with the deuterium, and that is the expected answer for this question. In question 3, 1H NMR spectrum of a compound of molecular formula C4H6 exhibited only singlet at 1.8, and the four compounds they are provided over here. It is a very easy question. We can tackle it by just identifying the types of protons in a compound. In a compound 1 butane, over here we are observing this will have, this is the first kind of proton, this is the second, and this is the third. So this compound is having the three different kinds of protons. So we do not expect a singlet or only a singlet. So in a compound B, as we are having the two CH3s and we do not have any alpha hydrogen, so definitely all the these two equivalent CH3s will give a singlet. So this is one of the thing that we may expect, and of course 1.8 delta that is corresponding to this. So this may be our probable answer. Before to this, it is always advisable to just look at the other options. In option C, we are observing over here, suppose we'll write the corresponding hydrogens, then we'll get that this is, so here we are observing if this is a symmetric compound, then this is one kind of proton that both the CH, it is one type of proton. So this is first and this is the second. So of course we'll find two absorptions, and in this case we do not expect only a singlet. So here we will get two absorptions, so therefore this is not a choice. In a compound D, again we'll observe here this is a CH and these two CH2 functionalities. So again this is a one kind of set of protons, and this is the second set of protons, so two absorptions, so this is not the correct choice. So as per we are having the three options, out of this the option B, it will show only singlet, and that is the correct answer. In question 4, the 1H NMR spectrum of paraxylene consists of, and four options are provided like this: 5 singlets, 1 singlet and 1 doublet, 1 singlet, 1 singlet and 2 doublets. This is the structure of paraxylene. Here we are identifying again this structure is having a symmetry. So if we divide this molecule through this plane, then we'll get two equal halves. So this is the detailed structure where we are finding if we are dividing the molecule through this plane, then we'll get the two halves, and we'll easily identify these two CH3s, they are identical, and these two CH3s, they will be singlet for 6 hydrogens. And if you are observing all the protons or aromatic skeleton, all are identical, and therefore all the four protons over here, that this is the 4 HA, that they will also give a singlet, and it will be corresponding for 4H. So the correct answer is we'll get the two singlets for this compound. In question 5, organic compound of molecular formula C4H8 exhibits only singlet at 1.9, and the four compounds they are provided like this. So same thing will apply over here. In this case we are seeing this molecule, that option A. So here we are having the four carbons and they are connected like this. So if you are considering this CH2 CH3, then by just looking toward the structure, that we come to know that this is associated, this will be the first kind of proton, this will be the second, this will be third, this is the fourth, and this one is the fifth. So this will have 5 different absorptions, so therefore this is not the correct, because we are in search of a compound that gives only a singlet, which is not possible in A. In B, we are identifying these two CH3s because this is a symmetric structure, and here the these CH3s, they will give doublet with the CH, and therefore that is not the expected from this one. And of course, this two CH, and they will give a quartet with the CS3, and they will both the CS they will give a singlet with respect to if you consider this A and H prime. So both this, yeah, we can write like this: these two CS3s they will give a doublet, while these two H A and H prime they will combinedly it will give a quartet. So therefore, this is not the expected answer for us. In a compound C, again this is the same. This is the compound that is having symmetry, and these two CS3 they are equivalent. So therefore, again these two CS3s they will give a doublet, and which is not expected from this. So this can be easily ruled out. So such problems we can rule out by just having one of the absorptions. So in this case, since this CS3 will give a doublet and which is not expected in the compound, so that will get ruled out. In option D, here we are observing that this is the compound where we are having these four CS2 connectivities, and all these protons they are equivalent. All these protons are equivalent, and we do not expect that the protons which are having a very small difference in a chemical shift. Here the chemical shift is change in the chemical shift, or the difference in a chemical shift is a zero. So therefore, this four set of, that is the total eight protons, it will give a singlet. So the correct answer for the compound for the question 5, that is option B. Dear students, I hope this material will help you, guide you in understanding the basic NMR problems. In the continuation of this discussion, we'll take a few more examples that will guide us in understanding how to relate chemical shift, coupling constant, and other complexities of 1H NMR spectrum in detail. At the moment, share the channel and the content with your friends. Thank you so much. Take care.